Good morning. Today we're going to take a look at how we can actually use the QuickSort algorithm so we can do some sorting with that. We have a quick recursion demo application that we've put together here, and we can see right here, I can do a basic QuickSort right here. And I click on the button and it does a original array, and then it has the sorted values. You can see those values are actually sorted. I have a random QuickSort where I can pass it a parameter of information, and it'll create an array that big and then sort that information. And I can just give a nice large value right here, say 40, and randomly QuickSort that, and you've got the results on that, and it randomly gets a value of that sorted right there. Let's go ahead and let's take a look at how we can actually do that sort itself and what's happening behind the scenes as we actually sort the information and create this SIP. So let's go ahead and take a look at a recursion demo class. As you can see right here, I have a collection of static methods, so we can actually practice using recursion as well as using static methods, because one of the benefits of recursion, one of the ideas of recursion, is that we have that static information that we have available to us because all the information is sent to the parameters. We don't have to maintain any state, so we just have a collection of static methods right here that we can use and demonstrate that. And so we have one public-facing method, the QuickSort algorithm right here, and that QuickSort algorithm right here takes an int array as a parameter as well as a low and high indices that we can use to start that. And it compares to see if the low index and the high index to see if low is less than high index, because it's going to stop once they actually meet at that point. If they don't meet, however, we're going to create a partition point, which is going to call partition algorithm. We're going to use passing it source, low index, and high index, and then we'll recursively call the QuickSort algorithm. Okay, we're going to split this problem in half. We're going to have two different parts of the solution. We're going to put those parts in half to actually do then the QuickSort again, which will of course call the partition algorithm to get to do the work on that, and break that down until we get to the point we have an actual sorted data set. First part we have is the partition algorithm. So we have our partition algorithm right here, so you can see that. And so it's a static method. It's a private static method because it's called internally from that external facing static method right there. It takes the same parameter sequence of int array source, low index, and high index, and because it's an int array, of course, it's an object, so we have a reference to it, so that's the same array we're talking about the entire time. But the indices we're talking about, because their ints are just copies of whichever value we're actually looking at, to reference those different parts of the array as we go through that. The first thing about this QuickSort implementation we're working at is we're using the single partition style. We're using the high partition, where we use the value of what's ever at the highest index we're working with as that partition point. And so I get the pivot value of what's at the high index. I then assign to my small index variable low index minus 1. So I'm going to start below where I'm actually starting with. And so right now, with the first call of this with 0, it's an invalid number because I have to actually go and increase as we go through it, as I can bring my actual partition as I go through and I meet it so it gets closer and closer to the actual point where I have, instead of splitting the problem in half, I get to the point where it's actually the same problem we're solving with that. Then I have my single loop. So unlike our other loops we've been working with, and when we're sorting data, we use a nested series of loops. When we're talking about these recursive outcomes, we have a single loop we're working with on this. And so I have for int index is set to be low index. So I start with that low index value that is set as the first parameter. This is the first int parameter inside that. And I'm going to go index is less than high index. So I go up to, but not including that high index value that I'm actually hitting. And index goes up by 1. And so if my source subindex is less than the pivot value, that high value that I started off with, I have as my first comparison value, then I move my small index, that reference variable, and move it up by 1. And then I'll call the swap method, which uses a standard approach to swapping, where it simply just takes what's inside the first parameter, puts it to the second, and puts what in the second parameter and puts it into the first. We have to use 3 lines for that though, because we have to only hold one thing at a time. And so I'm going to swap that as I go through, which does that quick little swap. So if its value is less than that point, I swap those values as I go through. So I then, at the one point, I have that swapped. And then after I've finished all of that loop, going from the int index of low index up to, but not including high index, I swap all the values. And then at the final statement of that, I swap what's at small index plus 1, where I'm at above one step beyond where I'm at, with what is currently stored at high index, that value was inside pivot value. And so I'm going to swap that value at that point and return small index plus 1. So I'm going to return to one spot past my pivot, so I can then break the problem down again on that, which then of course would come down to here. So I have that partition point that is created, and that's where I send to QuickSort. I send source, low index, and that partition point minus 1, which I just calculated at this point, and then source partition point plus 1, again from the original value. And because this is a recursive method, we're going to be calling the QuickSort from here, which will come back up to this point, passing it the original array, that new low index, which is low index, and my high index will be partition point minus 1. It'll compare those values to see if they are if they're less than. If that's the case, it'll recalculate the new partition point, passing it that low and that high index, which was that original partition point minus 1, and then call these two methods again, which builds that, breaking that problem down in half over here. We have half the problem sent to this call, and half the problem sent to that call, and repeating that process again and again until we get to the point where we have that values of low and high matching with that, so we can have those open with that. And so that's how we have the partition work within that, and we can go ahead and have an algorithm that can break the problem down into small pieces and sort those results. We can go through and do a step-by-step of this algorithm and actually trace all those pieces with that, but this is just a quick breakdown of how we can actually use QuickSort to process this idea and demo it right here. And then again, to use that here within our GUI project, we just pull it back up right here. I take the parameter I supply as a parameter right here. So I say 35. I call the random QuickSort. It creates a random array of 35 different values, ranging from plus or minus 100. I then sort those values accordingly, where it gets those values over here. So the QuickSort algorithm, it grabs the information, it calls the generate random values method I just sent to that. I take the original values, I parse that out as a string using the arrays.toString method. I then use the recursion demo QuickSort, where I pass it that array 0 and length -1, so I can pass it that highest valid index. I then output the sorted values using again that arrays.toString, so I can grab that information and put it inside that. I hope this is a good review of the QuickSort algorithm and how we can actually use it to sort data using ints as a basic idea, but you can use the same approach using any other data type, especially if you use the comparable interface, and take this and go further and understand this and do even more with this. And have a great day and keep working with recursion. Cheers, see you next time, and have a good day. Bye-bye.